Ever find yourself wondering, like, how the universe really ticks, at its core? Like, what makes everything run?
Yeah.
Well, that's what we're diving into today. The mind-blowing world of thermodynamics.
It's everywhere.
It is everywhere. And to help us navigate this, we've got the one and only Richard Feynman,
Oh, the best.
specifically his lectures on physics, chapter 45. We're going deep on thermodynamics. You ready for this?
Absolutely. Let's do it.
Yeah.
Feynman, he just has a way of making even, the most complex stuff
Yeah.
feel so understandable.
Like an engaging puzzle.
Exactly.
So our goal today is to move beyond just knowing the terms like enthalpy and entropy.
Yeah.
We're going to break them down
Yeah.
and actually, wrap our heads around how they're woven into, well, everything around us.
It's all connected.
It really is. We're talking that steaming cup of the pressure in your car tires, the energy in a battery, even how scientists figure out the temperature of stars trillions of miles away.
It's all related. It's amazing.
So, to kick things off, Feynman starts us off, kind of surprisingly, with this thing called partial derivatives.
Okay.
But before you hit that skip button thinking, wait, I didn't sign up for like a calculus lecture, I promise it's way more interesting than it sounds.
He makes it very accessible.
He does, and he does it using this car analogy. So imagine you're cruising along, right?
Okay.
And you're going uphill, and you want to know how much your speed changes just because of that hill.
Right.
But your speed isn't just about the hill, it's also about how long you've been driving.
Exactly. Yeah. How much time has passed.
So it's like, how do we isolate the effect of just the hill?
Exactly. That's what partial derivatives do. They help us isolate that one variable, like the hill, and see its impact.
Right.
As if everything else, like time, is on pause.
That's such a good way to put it.
Yeah.
It's like saying, okay, for a second, let's just focus on how much this hill is affecting my speed, ignoring everything else.
Exactly. It's a way to understand how one thing influences a bigger, more complex system. And Feynman uses this to introduce the real stars of the show: internal energy, heat, and work.
Okay, so these aren't just some abstract, like, physics textbook terms, are they?
No.
We experience them all the time, every day.
Absolutely.
Think about the warmth you feel from a fire.
Yeah.
That's heat, right?
Yeah, heat, that transfer of energy.
It's a form of energy transfer, or like the effort you put into blowing up a balloon.
Oh, yeah.
That's work. You're changing the energy of that balloon.
You're putting energy into the system, and that's changing its internal energy, like the energy of the air inside.
And those concepts, all of them, are linked by this fundamental law, this kind of like, overarching principle called the first law of thermodynamics.
The cornerstone of it all.
So what does it basically tell us in a nutshell?
In the simplest terms, energy can't be created or destroyed, just transformed from one form to another.
Oh, so it's like a, universal accounting system for energy.
That's a great way to think about it, yeah.
Okay, so then Feynman, he takes us a little deeper into this world, introduces this thing called the Carnot cycle,
Okay.
and he asks us to picture a simple engine, the kind with a piston moving in a cylinder.
Like a classic car engine.
Yeah, and to help visualize this, he uses this thing called a pressure-volume diagram. What is that?
So it's like a graph. It tracks what's going on inside the engine, how the pressure and volume change as the piston moves.
Okay, so it's like a visual representation of the engine's every move.
Exactly.
And this is where it gets really, really interesting, because the area inside that graph, the area within those curves, it represents something really important.
It represents the work done by the engine. The bigger the area, the more work the engine is doing.
Wow, that's so cool. And this is where Carnot comes in.
This is it. This is where he made a groundbreaking connection. He found a link between the work done by that engine and the heat absorbed at a constant temperature. It's a huge deal.
Okay, so break that down for me. How does that, seemingly simple relationship, how does that change how we understand engines?
Well, Carnot's work, it revealed the maximum efficiency you could ever achieve, like the absolute limit on converting heat into work.
Oh, wow.
And this principle, fundamental to how we design not just engines, but refrigerators too.
That's incredible. Who would have thought that something so, seemingly straightforward could have such huge implications?
That's the beauty of fundamental laws. Often their applications, they pop up in the most unexpected places.
Okay, well, speaking of unexpected places, prepare to have your mind blown.
Okay.
This equation that we're talking about, this equation derived from a simple engine, can actually be applied to, wait for it, rubber bands.
Rubber bands. That's kind of wild, right?
It seems crazy. How on earth?
It all goes back to energy. Remember the ideal gas law from, like, high school chemistry?
Vaguely, it's coming back to me in pieces.
Right, so it describes how pressure, volume, and temperature are all related in gases. Now, those gas molecules, they're bouncing around creating pressure. The forces between those molecules, they explain why pressure and volume change.
Okay, yeah, I'm following.
The fascinating thing is those forces have a parallel in the long-chain molecules that make up, you guessed it, a rubber band.
So just like with gases, changing the temperature of a rubber band affects those forces between the molecules,
Right.
which then changes its length.
Exactly. Heat up a rubber band, and what happens? Those molecules, they start jiggling around more, causing it to contract.
Oh, that's super.
It's a perfect example of how thermodynamics links heat force and length, even in something as ordinary as a rubber band.
It really is, and it just keeps blowing my mind how these connections pop up in the most unexpected places. Like, who would have thought something as everyday as a battery could be explained by thermodynamics?
It's true, the change in voltage of a battery, as the temperature changes, can tell us a lot about what's happening chemically inside. It's like your phone battery is a tiny chemistry set constantly in flux following these fundamental principles.
That's wild. So we've gone from rubber bands to batteries, and now, get this, we're going to something astronomically huge.
You're talking about blackbody radiation.
Yes, blackbody radiation. It sounds like something straight out of Star Wars.
Right.
But it's how scientists measure the temperature of stars that are trillions and trillions of miles away.
It's incredible.
How is that even possible?
Okay, so imagine heating a piece of metal.
Okay.
As it gets hotter and hotter, it starts to glow, right?
Yeah, first red, then orange, then like white hot. I've seen that in those blacksmithing videos. It's mesmerizing.
Exactly. And stars, they're doing something very similar, but on a massive scale.
Oh, wow.
They emit light across a whole spectrum of colors, and the exact mix of those colors tells us their temperature.
So by analyzing the light from a star, we can figure out how hot it is.
Exactly. And the key to understanding that light is understanding how energy is spread out at different temperatures, and that, my friend, is a core concept in thermodynamics.
It's incredible. Okay, so we've covered rubber bands, batteries, and even the temperatures of stars, all thanks to thermodynamics.
All connected.
It's like we've been given this new, amazing way of looking at the world. But I gotta admit, some of these equations can be a bit intimidating.
Like, which ones are tripping you up?
Well, like that one about the change in internal energy of a system.
You mean the one that says the change in internal energy equals the heat added to the system minus the work done by the system?
Yes, that's the one. It always seems so simple, but I feel like I'm missing something crucial.
It's actually a very profound statement about energy conservation. Think about it this way. You can pump energy into a system by heating it.
Okay.
And that system can then use that energy to perform work, like pushing a piston in an engine.
Gotcha.
But the total energy, it always has to balance out.
So it's like that universal energy accounting system we were talking about?
Precisely. And that same accounting applies whether we're talking about simple steam engine or the insanely complex chemical reactions happening inside a battery.
That makes so much more sense. Now, what about that Clausius-Clapeyron equation? I remember struggling with that one back in my chemistry days.
Ah, yes. That equation, that one helps us understand the relationship between pressure, temperature, and those changes in the states of matter, like when water boils.
Right, liquid water transforming into steam, a classic phase change.
Exactly. And the Clausius-Clapeyron equation gives us this mathematical link between how the pressure changes with temperature and the amount of heat needed for that transformation to happen.
So we can use it to predict things like the boiling point of water at different pressures.
Precisely. It explains why water boils at a lower temperature at higher altitudes where the air pressure is lower.
Oh, that's why it takes longer to cook pasta in the mountains, right?
Exactly. The lower boiling point means your water is cooler, so your pasta takes longer to cook through.
Wow, I never knew there was a thermodynamic reason for that.
There often is. But here's where things get even more interesting. While thermodynamics gives us this incredible framework for understanding energy on a large scale, it doesn't really dig into the microscopic nitty-gritty of how those transformations actually occur at the atomic level.
So it's more about the big picture, the overall effect.
Exactly. And that's where statistical mechanics comes in. It bridges that gap between the macroscopic world of pressure, temperature, and volume and the microscopic world of atoms and molecules.
So it's like we can zoom in and see what those trillions of individual water molecules are doing as the water boils.
Precisely, imagine them all jiggling around with a certain amount of energy. As we add heat, their average energy increases, they jiggle faster, and eventually they break free from their liquid bonds and become steam.
So it's like a microscopic dance party happening in that pot of water.
I like that.
And the Clausius-Clapeyron equation gives us this amazing way to connect that invisible dance party to the very visible act of boiling.
Exactly. It's incredible how these different levels of understanding, from what we see with our own eyes to the behavior of tiny atoms, all come together in thermodynamics.
It really highlights just how much is going on beneath the surface of what we can observe every day.
And we're just scratching the surface thermodynamics with its elegant laws and seemingly endless applications. It's everywhere, from how our cars run to how power plants operate.
To the very existence of stars.
It's true. And the most exciting part is that we're always discovering new connections, constantly pushing the boundaries of what we thought we knew about the universe.
It really makes you realize just how much is happening all around us that we just totally take for granted.
It really underscores the power of physics, doesn't it, to reveal these hidden connections in the universe.
Absolutely. It's like we've been given this new way of seeing the world.
Totally.
And, while we've been focusing on Feynman's work and his insights, it's important to remember that thermodynamics, like any field of science, it's built on the work of countless brilliant minds throughout history.
That's right. From Sadie Carnot, who really pioneered the field with his research on how efficient engines could be, to James Clerk Maxwell and Ludwig Boltzmann, who developed all those crucial tools of statistical mechanics. It's been a team effort, a true journey of discovery.
And Feynman, with his incredible knack for taking these really complex ideas and making them accessible to anyone, he lets us feel like we're right there on that journey with them.
Exactly. He brought thermodynamics to life for a whole generation of new thinkers.
He really did. And it's a journey that's still ongoing, right?
Oh, absolutely.
There's still so much we don't know about the universe and the laws that make it tick.
And that's what makes it so exciting.
Right. Every new discovery, it just leads to more questions, even more avenues to explore.
It's like we're constantly redrawing the map of human knowledge, pushing those boundaries further and further out.
And who knows what mind-blowing applications are still waiting for us out there as we dig deeper into these fundamental principles.
That's a great point.
It really is. So as we wrap up this deep dive into thermodynamics, I don't know about you, but I'm left with this overwhelming feeling of awe just thinking about how elegant and interconnected everything in the universe really is.
It truly is all around us, just waiting to be discovered.
Exactly. So next time you see a steaming cup of coffee or feel that warmth radiating from a fireplace or even just stretch a rubber band, take a second and really appreciate the invisible forces that are at work right there.
It's amazing when you think about it.
It is, because behind those everyday experiences are the fundamental laws of thermodynamics, quietly orchestrating this incredible dance of energy that makes our universe so captivating.
It's a beautiful thought.
It really is. Thank you so much for joining us on this incredible journey into the heart of thermodynamics. And until next time, keep those minds curious.